we talked about this fellow Weil in German, Whale, okay? And he's got a couple problems because he's a mathematician. Well, he died already a long time ago. But he wrote a book, and I think here I've got the book somewhere. Oh, no, I don't have it. Here it is, maybe. Let's see if this is it. Yeah. And he wrote a book. It's called Spacetime Matter, okay? And he, in that book, he starts out with geometry, the rudimentary of geometry, and he starts out saying what a point is, what a line is. And this is going to be important for the issue of the axis of rotation or spin of the moon. Some people say, you know, whether the moon spins or not. And so what Whale did, he says, he defines what a straight line is. He says its distinguishing feature is that it is determined by two of its points. So if you have 2 points, right, you have a line. Thus, if A and B are 2 different points, the straight line G equals AB includes every point. In other words, every point in between. I don't know where he got the extra points. He put them in there by hand. But essentially, he's not talking about points. He's talking about locations. They call them points. Why? Because they're going to represent them with a dot. Okay? And he says the straight line lies evenly between its points. Expressed kinematically, this is tantamount to saying that we regard the straight line as an axis of rotation. Okay, so he's got these row of apples. That's a notion of row of apples. But then further on, he screws up completely because he has a different notion of what a straight line is. He says we may say that a straight line is derived from a point by an infinite repetition of the same infinitesimal translation in its inverse. So he's going to talk about motion of a point, motion of a location, if you can imagine that, a location that moves. Very scary stuff. And that's different than the row of apples. So we're talking about an itinerary. And he calls both these notions, these irreconcilable notions, he calls them lines, okay? And so the question is, which of these two is going to be the axis of rotation? Is it going to be the row of apples or the itinerary described by one apple? Okay? He says a plane, however, is derived by translating one straight line, okay, along another. In the case of rotation, for example, the points on the axis are distinguished by the property that they preserve their positions, okay? So we got a problem with several notions here. And it's essentially what's wrong with geometry, which is an attempt to merge the language known as mathematics with the science known as physics. And those two will never meet. They have nothing to do with one another. And that's where the problem is. Geometry was the first attempt that our ancestors, way back when, they tried to merge these two things. They said, look, let's take mathematics. Let's measure the land, because that's what geometry means. The measurement, essentially, that's what it was used for, measuring the land. And they started doing calculation, they started doing measurements, and they related it to physics because they were measuring something physical, you know, the land in this case, or it could have been a building or whatever. So this is how mathematics got merged with physics. And the problem there is that you have the point, and they had to create this monster called the point. And the point, they say today that it's an undefined notion, concept, whatever. And why is it undefined? Why do they say that? Well, they say that because the point, they say, is zero-dimensional. Or like Euclid said, that which has no part. Right? So we have this zero-dimensional, no-part point. And you say, okay, what is a point? Well, it's a dot. It's a dot, and the dot is either 2-dimensional or 3-dimensional. So we have a zero-dimensional point represented pictorially by a 2- or 3-dimensional dot. And is the dot the point? And they said, no, the dot is actually representing a location, a non-dimensional location, because a location has no dimensions. It's not a physical object. So we have what? Let's see if we got it straight. We got a dot that is 2-dimensional or 3-dimensional, representing a concept which is non-dimensional, and they call that a zero-dimensional point. And it doesn't stop there. Then they take that point, like Mr. Whale did, and he goes in there and he takes this dot, this zero-dimensional point, and he constructs a 1-dimensional line. Yeah, you heard right. We got zero-dimensional points, nothing there, and it's going to construct a 1-dimensional line, which is also nothing. And the question is, are we looking at a row of dots? Are we looking at a row of locations, meaning motion? What is a line? This is the problem. We don't have a good definition. That's why they say, well, we don't know. We don't have a definition for line. We don't have a definition for point. We don't know what it is. Of course you don't know what it is because you mixed an abstraction with something solid, which is the dot, right? In one case, in the other one, you take a plane, which is this elongated rectangle known as a line, and you're representing which is two-dimensional, and you're representing a one-dimensional concept known as a line. Okay, what is the problem with all this? Well, the problem comes when we do spin. We talked about the spin of the moon, and people don't know whether the moon spins or not. And here are the different possibilities. We have three types of people. We have the flat earthers, okay, and they believe that humans did not go to the moon, did not even go to space. Okay, and they say humans haven't gone to space because we can't make it there, right? One of the reasons is that they say that we have radiation, vacuum, and temperature. And we have the Moonies. They say usually the same thing, that those are the reasons we haven't gone to the moon. They do believe that we went to space. A lot of these Moonies are not flat earthers, and they do believe the Earth is round, etc., etc. But those are the two groups. But then you have the third group, which is what I call the Loonies. Okay, we have the Moonies and the Loonies. The Loonies are people who believe the moon spins. Okay, and no, the moon does not spin. And the question is, why have the mathematicians never discovered that? Well, they never discovered it because they never defined the word spin. That's what it comes down to. Their definition is no good, especially for physics. And that's why you never leave a mathematicians define things for physics, okay, because they have no clue. What's the issue? The issue is that, like Mr. Wales said, a one-dimensional line cannot be used in physics. And what they do is they use this concept of mathematics, which we don't know if it's a row of apples or an itinerary of an apple, okay? And I think I have one here. Yeah. So we don't know if the axis that they talk about, the one-dimensional axis, is this, is it a row of apples or is it an itinerary of an apple? Is it 2 points which have many points in between? If the points are locations, are we talking about motion? Are we talking about dots? What is this? What is a line? What is this famous axis? And no matter what I put in there, it's not one-dimensional. In fact, no one can come up with a one-dimensional anything. Okay, this is the issue. No one can come up with that because people say, well, I can imagine it. No, you can't, because if you can imagine it, hey, very simple. Show us a piece of your mind. Okay, that's what you got to do. Okay, and so that's the issue of that. That creates problems when people try to figure out whether the moon spins or not. Okay, does the moon spin or not? And in the case of mathematical physics, they say, yeah, the moon spins. And you say, well, why does it spin? Well, because it rotates around the Earth in 27 days, and so it made one full turn around its own axis. It spins very slowly, but it does spin. That's the argument, that's the logic, if you can call it logic. And no, the answer is no, the moon does not spin. Okay, and the question is why? Well, we have to define what spin means, and for that you have to look at this axis. And the problem there is the question whether the axis itself spins. Does an axis spin? And of course, if you have a one-dimensional axis, which you cannot even imagine because you can't put it on paper, you can't bring it to the conference, you can't bring a one-dimensional anything, put it out here for us to see it objectively and have an idea what you're talking about. Well, much less, if you can't put it out here, much less can you talk about it spinning on its axis. Does the axis spin on its axis? That's the question. Okay, why is that important? Well, because the mathematicians, when they talk about spinning and angular momentum and all this other stuff, they don't even look at the axis at all. They're not interested in the axis per se. What they're interested in is distance, and not even distance traveled. What they want to know is how much distance, how much separation is there between the so-called axis, which they're going to use as the frame of reference, to the edge of whatever, to the surface, point on the surface, a location on the surface that's going to be supposedly rotating, spinning. Okay, so they're just going to look at distance. Does the distance change? That's what they're going to be looking at. And the question there is, if the distance does not change, the thing cannot be rotating. If the distance changes, then the thing is rotating, spinning. Okay? And so the question there is, you need to know whether that axis is spinning as well, because with a two-dimensional or three-dimensional axis, you can talk about the spinning of the axis. If I drive a stake right through the moon and I keep it steady, God's stake, just a little cylinder that I drive right through the center of the moon, does its rotation around its orbit, actually, around the Earth, 27 days, does the moon at any point change any of the locations on its surface with respect to that axis if the axis is standing still? And the answer is no. The moon moves together with the axis. So if we were to look at that, I think I've got a picture here. Okay, yeah. This is what you would see. You would see that the one that's wrong there, the red one, okay, the one on the upper right, that's not what happens with the moon. The moon would rotate like the one on the left, where the axis turns together with the moon. Okay, because that's the moon always shows the same face to whatever point on the axis you want to select. It always has the same distance, no matter what, when it turns around the sun. That's different than the Earth, which changes locations on its surface with respect to a fixed axis. So the moon doesn't spin like a top, not at all, slowly or fast at all. It always has the same point on the surface, pointed to the same location on a three-dimensional axis. On a one-dimensional axis, we don't know, because there is no such thing as a one-dimensional axis. You cannot imagine a one-dimensional axis spinning on its axis. And so it's pointless to talk about the one-dimensional axis of mathematics. And again, it's because they introduce concepts into physics that we have these problems where people say, well, does the moon spin or not? Well, you can't use the concepts of mathematics, especially when spin is a physical phenomenon. It belongs exclusively to physics and not at all to mathematics. Okay? And then you have the issue, where they have atoms where they say the electron spins. And you say, okay, it spins like a top, you mean? And the answer is no. Spin is a number that we assign to spin. We assign minus half, we assign plus half. We have all these values for spin. Does your top have a half spin? Or a positive half spin, minus half spin, a one spin? What spin does your top have?